So we're going to do this interactively. Our speaker this evening is Dr. Nathaniel Frizzell. Is a professor at the University of Scranton in Eastern Pennsylvania. And Nathaniel, it's one of these things that I guess looks can be deceiving. You look like you're about 14 years old.
I guess so, yes.
But
I
you're
get
not.
that a lot. That's right, I'm not.
But you're not. And
No.
so tell us, Nathaniel, before you start your presentation, a little bit about your background, about being an Eagle Scout, and how you got started in amateur radio, and also your education.
Sure, thanks a lot, Tim. So my name is Nathaniel. I'm W2NAF, and I was introduced to amateur radio at a Jamboree on the Air weekend back when I was in about 7th or 8th grade. And I remember going to Camp Glen Gray, which is in New Jersey, on a cold, wet, rainy weekend in October. And I remember seeing this old guard cabin there, and Greg Nitkowski, N2BSA, was in there, and he had his TS-430 set up and attached a little dipole out of the cabin. And I just remember hearing the static and hearing him talk to these places, faraway places, and it just captured my interest. So then I just stuck with it. I ended up getting my ham radio license, the first part of it, the novice portion at the 1997 National Scout Jamboree at Fort E.P. Hill in Virginia, and actually finished my license a year later. And I enjoyed it through high school, and then I taught at a scout camp, Forestburg Scout Reservation, during my summers in college, and I started W2FSR there. And that's when I decided to eventually go for electrical engineering. I was a music education major at the time, and then I decided I really wanted to do more electronics and radio. So then I added a physics degree, and then I went to get my PhD in electrical engineering at Virginia Tech, and I ended up in the SuperDARN radar group there, which is a group that studies the ionosphere using HF radars. That's how I got my PhD. And then, I'll talk a little bit more about my history in the talk today, because I'll talk about how I connected the ham radio with my science work and what I study today. So that's kind of it.
So two things. Nathaniel is a recent winner of the Ham of the Year, as awarded by the Dayton Amateur Radio Association, the host of Hamvention. And Nathaniel is also is the founder and lead organizer of a group called HamSCI. And you'll hear more about HamSCI here this evening as his talk progresses. So Nathaniel, welcome to the Mercer County Amateur Radio Club, and the floor is yours.
Thank you so much, Tim. It's a pleasure to be here this evening. Let's see, I'll share my computer sound here, start this up. And, as I'm giving the talk tonight, if anyone has questions along the way, feel free to jump right in and ask your questions, and I'll be happy to answer and dialogue with you. Let's see, so I'll swap that. How does that look for everybody? Good? Great. Okay, so today I'm going to talk about HamSCI, the ionosphere from your backyard. And so, yeah, I'm Nathaniel, W2NAF, and I just gave a little bit of my history. I'm currently an assistant professor of engineering and physics at the University of Scranton. And so I'm going to talk about how we can combine ham radio and science and hopefully benefit both. And I wanted to start off by saying, I really came to science. The reason I ended up doing science was because of ham radio. And so I wanted to spend a few minutes talking about ham radio, which of course everyone here knows really well. But it really is truly an amazing hobby with so many facets. And these are just a few of the different things that I've been able to be involved with through ham radio. Most recently, you see up here, W3USR. Here's my building at the University of Scranton. And there's actually now a DX Engineering magnetic loop RF Pro 1B up on that ladder. And hopefully eventually there will be more antennas up there. But we just started this club this year, so we just got this call sign this past July. So that's very exciting. We now have the Scranton group there. Some people are interested in building electronics projects. This is John Ackerman, N8UR's precision time interval counter. He's one of those time nuts sort of people. AB4EJ, he's into HF. I have a lot of HF stuff in here because that's really my passion too. So he's one of my friends. Of course, operating Field Day. I've worked at National Scout Jamborees. I've gotten to go to far away and exotic places, which I'll talk about in this talk as well. So here's when I went on a trip in graduate school to help build this radar system on Adak Island. Here's a rather modest station in Western Pennsylvania that, you know, they want, you know, he's able to get out of the country into Europe with these antennas or so. So he's a nice little station over there. And then this is from my time at NJIT, working with some of my students there. And this is the K2MFF station, which has been running for many years. And hopefully at Scranton, we'll have something like that in the future. So how is all of this connected with space weather? Well, as HF radio especially is allows us to have global communications, but only under the right conditions. So the ionosphere has to be in the right conditions. And if that's true, then you're able to talk from one place in the world all the way over the horizon to the other side of the world and back. And the ionospheric state is really controlled by the entire geospace system. So this shows the main drivers of that system. We have, of course, the sun, and it sends out a solar wind and carries with it an interplanetary magnetic field. And you can have coronal mass ejections and solar flares and all sorts of other phenomena that happen out here and can impact the Earth's magnetic field. And if you watch Tamitha Skov, the space weather woman, she talks a lot about what's going on out here, and she does a great job with that. And so those impacts can hit our Earth's magnetosphere and interact with the Earth's magnetic field. And so you can actually have energy enter into the Earth's magnetic field. You can have these field lines be pushed around to the night side. You can have particles end up flowing back down along these field lines into the polar regions, creating the aurora. This can cause convection, actually. Motion in the magnetosphere can cause motion in the Earth's ionosphere as well. So there's all sorts of interesting processes that will end up affecting our ham radio signals. One thing I don't show on this slide very well is that we are also learning that influences from the lower atmosphere, from the neutral atmosphere, from terrestrial weather can also rise up and impact the ionosphere too. And so hopefully I'll get to talk a little bit about that this evening as well. But either space weather from above or weather from below, that all can affect our propagation. So as a graduate student, I have been fortunate to go to many faraway places. And the reason, and many of those places were quite cold. And the reason for that is, again, back to this picture, you have these magnetic field lines and they go into the polar regions. And so it turns out that charged particles out in space, they will follow along magnetic field lines similar to wires. And that's why you end up having the aurora there. And as those particles precipitate from space into the upper atmosphere, they'll cause ionization there. And if you're able to either study the aurora or study the ionospheric impacts in that particular region, you're able to learn a tremendous amount of interesting things about the physics, not only in that region, but also far out into space. It actually is a form of remote sensing to the entire larger space environment. So that's one of the reasons that we have so much space physics instrumentation in places like Antarctica. So I did get to go to McMurdo Station, which is right down here. It's the largest US station. And you can see here's a statistical auroral oval here. And here's a recording I made from their ham radio station, KC4USV, back when I was there. You're able to hear that? What did you notice about the tone of the CW there? Did anyone notice anything funny about the tone of the CW?
Sounded like Aurora.
Yeah, it sounded like Aurora because our signals were in fact passing through. And so, you know, not only one of the things you get out of that is that if you're able to study those pitch fluctuations or those frequency fluctuations in that incoming signal, you can actually learn something about the ionosphere between you and the station that is transmitting to you. Let me play that one more time. You get some sort of sense about how fast the ionosphere is changing, because that's what you're basically hearing. You're hearing changes in the path length, the propagation path length with time, causing these pitch changes. Oops, let's go back. There you really hear it go low. There it stabilizes again. And that's my side tone again. So you can really, in certain circumstances, you can really hear the space weather effects in a very dynamic way. So another one of my trips was out to Adak Island, and that is in between Russia and mainland Alaska. So this is a US island, but it's actually, I think, the farthest west actual town in the United States. So it's actually farther west than Hawaii. And it's also the most southern town in Alaska. So it's a very interesting place. And it's a very rainy, harsh climate there. So here's a picture. There's the HF radar, SuperDARN radar we built while we were out there. And you can see Mount Moffett in the background. And there I am, helping to put the transmitting rack together. And there's my friend Kevin, KJ40AP, trying to rescue our temporary ham radio antenna in the middle of one of these storms. And over here is our station that we brought with us, our portable station. But one of the things I really got out of this was it was that trip. I think this was back in 2012. That's when I first learned about the reverse beacon network. And I imagine that everyone here, or almost everyone here, is familiar with the reverse beacon network. Is that true?
Not necessarily. So you might want to talk about that.
Okay. So the reverse beacon network is a network of automated software-defined radio receivers that are constantly listening to the CW ham radio bands. And what they're doing is they're looking for, they will automatically decode the Morse code and spot you, reported on the spotting networks. So you basically have an automated spotting system. And Tim has you have a very elaborate RBN receive station over at your house, right?
That is true, yes.
Yeah, so if you're out in your area and you need to know what CW stations are on the air, you can just look for spots from Tim's RBN network. Anyway, the RBN very nicely archives all their data, and I'll show some examples of this in a little bit. They both bring it in real time and they archive their data. And I said, well, I bet we can see space weather effects in this data in a similar way to how we use the radar systems to observe space weather effects. And so it was Ethan Miller, K8GU. He's the one that introduced me to the RBN while I was on this trip. He's also another space physicist, and he was also out there helping us build this radar system. So that eventually led to, we were able to get some of that information published. And I think I have those plots later in the talk. But that eventually was one of the things that led to this idea of this ham radio science citizen investigation. And this is the idea that we have a collaborative that allows university researchers to collaborate with the amateur radio community in scientific investigations. And, our objectives are, one, to advance science research and understanding through amateur radio activities. 2, to encourage the development of new technologies to support this research, and 3, to provide educational opportunities for amateur radio community and the general public. And so that's where a lot of this comes from. And one of the interesting things is, you know, the way that ham radio operators think about propagation and the ionosphere can sometimes be very different than the way scientists
Kind of forward. I don't know how.
Oh, that's my mom there. Hello?
Hi.
Hi. Welcome to the meeting.
Thank you. Sorry, I didn't know. You're doing a great job.
Sorry about that. My mom is KC2KRQ. I invited her to come listen too. So, okay. So yeah, so scientists and ham radio operators, they can see, they both look at radio propagation in the ionosphere, but they sometimes think about it in very different ways, and they don't always, you know, realize or understand the way the other people are thinking about it. So for instance, I think everyone here, you know, knows about QRP radio, and that if the conditions are right, you can throw up, you know, a wire in the tree, and you can use just a few watts, and you have the potential, at least, of being able to talk to someone, you know, hundreds or thousands of miles away if the conditions are right. And we all know this. But I've actually talked to some scientist friends that, you know, aren't ham radio operators, and they might look at HF data all of the time in a visual format, but they didn't realize that you could use so little power, or, you know, really have such a random antenna orientation and still, you know, make it so far away. So that was actually a surprise to him. So this very, very experienced scientist, you know, learned something about that. And conversely, you know, many of the things we as amateurs, you know, maybe think or believe aren't necessarily true. So, you know, we're used to seeing these, we're used to characterizing all of our propagation by what the KP index says, or the what solar flares are, but it's so much more complicated than that. So somehow we wanted to get the two groups to be able to talk together, and that's where HamSCI is coming in. We're getting the two groups to talk together. So how can we use ham radio to help remote sense the ionosphere? Let's talk a little bit about how HF radio propagation works for a minute. And what you're seeing here is something called an HF ray trace diagram. So the background colors here, this is in what's called plasma frequency, but it's actually directly related to the electron density of the ionosphere. So as you go up on the y-axis here, this shows you altitude going from 0 to about 550 kilometers altitude. And then on the x-axis here, this is ground range on the Earth going from 0 to 2,500 kilometers. And so then right here in the middle, around 250 kilometers altitude, you see the peak, the F region densities. And this gradient in electron density can actually be converted into an index of refraction. And so, it's this gradient in index of refraction that causes this HF ray bending. So there are equations called the Appleton-Hartree relations, which will let you, if you know the electron density and you know the frequency you're operating on, and you know your takeoff angle, you can actually compute where the ray, predict where the ray is going to fall. And so this is a ray trace diagram for 14 megahertz for a ham radio transmitter in Florida, AA2MF. And it's connected to a ham radio receive station, Whiskey Echo 9 Victor in Wisconsin. And so you can see that right now we're predicting that there is in fact a path between the two stations. The computer's predicting that. One of the other things that's interesting is that this is very frequency dependent. So if you keep the same background electron densities, as you increase frequency, you'll get less bending, and as you decrease frequency, you'll get more bending. And so that changes this pattern. But that's why it's so important that we have so many different ham radio bands. We're not all just located. They didn't just give us, 100 megahertz worth of bandwidth at, say, at 30 megahertz. They've sliced and diced us up and spread us across now the low frequency, medium frequency bands, HF, and then VHF and plus. And that's because all of these different bands have different propagation characteristics and bandwidth capacity and things like that. So that's why we're split up like that. So if we're able to monitor what the propagation is around the world on all these different bands, we now have the ability to, potentially remote sense what's going on in the ionosphere. And so this is what I talked about before. We have these different ham radio observation networks. I talked about the reverse beacon network already. Many of you may also be familiar with WSPRNet, the Weak Signal Propagation Reporter Network, which was originally developed by Joe Taylor, and then PSKReporter, which is run by Philip Gladstone. And these systems are constantly monitoring high frequency communications on the ham radio bands, and they're archiving it to disk. And it's really neat. We now have data that's back to 2008, and that's a whole solar cycle. So, at the American Geophysical Union meeting this December, I'll be giving a presentation where I actually show the ham radio observations over this entire solar cycle, and you can see some interesting trends in that. So this was the first example of the of an event I published with the RBN data. And so here's the receive station that we have at the Jenny Jump Observatory in New Jersey. And here is the RBN observations for a 15-minute period on May 13th, 2013, between 15:05 and 15:20 UT. And you can see communications are fairly strong. There's, over that 15-minute period, there's over 1,100 communication paths being observed, and it's color coded by frequency. So the majority of the communications are happening on 21 megahertz or 15 meters, quite a few on 14 megahertz or 20 meters, and then spread throughout. And then so that's happening right around here. And then if you look right at 1605 UT, there is an X-class solar flare. And then if you look at the 15-minute period immediately afterward, you just see the communications drop off. And so that's a really neat result. This has actually been known about for quite some time, but now we're actually able to see it in the ham radio data. This is what we call a radio blackout. It's a case where this solar flare causes a sudden ionization of the D region ionosphere. And when that happens, that D region doesn't help refract or reflect our HF radio signals. It actually ends up absorbing them. And so you get a lot of absorption as a result of this flare, and that's why you get this radio blackout. But you'll notice that it mostly affects the daytime ionosphere, not the nighttime or the mornings or the evenings, because those parts of the world are shielded from the flare by the Earth itself. Here's another example of that on the left. This is from a couple years later, September 2017. Here are two solar flares, one at almost 9 UT and another one at almost noon UT. And here I have the data presentation a little bit differently. I'm looking over Europe here. So these are both RBN and WSPR combined. It's primarily WSPRNet. And you can see that there's a big heat map here. And the heat map is the midpoints between the transmitters and receivers, because that's where we're assuming that the ionosphere is affecting the signal. And then over here, you see a two-dimensional histogram with communications range, distance between transmitter and receiver on the y-axis, and then time of UT time on the x-axis. And we are showing 12 hours worth of data here. And so what you can see is things are going along just fine on all the 7, 14, 21, 28 megahertz bands, and then boom, right at 9 UT, you get a flare and you get a blackout. Things recover. And then you get another flare, and then you get another blackout. This flare is bigger, the blackout's a little bit longer. So you can really see these effects in the ham radio data. Now this, on the right-hand side here, this is an effect that most people here are probably much less familiar with than the solar flares, but it's just as real. And this is what we call a traveling ionospheric disturbance. And this is actually the subject of my PhD work, and I'm working on writing this up into a paper right now. So here, this is RBN and WSPR again, but this is actually over the United States, not over Europe. I have to come up with do a better job with this figure. But if you look on the bottom here with time, you can see how the range moves farther away, closer, farther away, closer. So what this is saying is that the distances that you can talk to are oscillating. And the reason for that is you're actually having a wave-like structure of in the electron densities in the ionosphere moving overhead over the United States. Down on the bottom here, these are what we call total differential total electron density measurements, and they're actually made using GPS receivers. So using a GPS receiver, you can actually get a measure of how many electrons are between you on the ground and the GPS satellite in the sky. And here you can see the peak of the electron density trough right here, these red and yellow colors. And then you see the trough down here, the blue colors, less electron densities. And then you see another peak in electron densities over here. So with time, this structure moves southeastward across the United States. And that's what's causing these oscillations. These are taking place over a period of, say, an hour to an hour and a half is the period of these things. So we can see these traveling ionospheric disturbances in the RBN and WSPR data as well. So a couple years ago too, everyone raise, if you got to see this total solar eclipse in 2017, I want you to raise your hand. Okay, great. Yeah, I can see you guys on the computer monitor here. So quite a few. Did any of you guys participate in the solar eclipse QSO party? No? Okay. So a couple years ago, 2017, we had a total solar eclipse that went all the way across the United States. And this was a very big deal. And the thing about the eclipses, solar eclipses, it causes almost temporary, almost night-like conditions. But there are differences between an eclipse night and like regular night. But it does, you get this darkening of the sky. And so you could actually imagine that this might affect the ionosphere as well, because the ionosphere is created by solar energy ionizing the upper neutral atmosphere. And so when you take that driver away, the ionosphere starts to recombine. You lose ion production. You tend to see a decrease in the electron densities up there. So we wanted to see if we could see that in the amateur radio data as well. And so we put together a solar eclipse QSO party, and we asked the following questions. Can we use HF ham radio communications to observe eclipse effects on the ionosphere? And can we use data model comparisons to better understand the ham radio data and to constrain or calibrate the model? And so we created a solar eclipse QSO party. I worked with people like Ward Silver, N0AX, and a number of others to put this together. We tried to make a science experiment that was as contest-like as possible. We wanted to just make it, feel natural for ham radio operators who like to do contesting to participate in this. So it was contest-like. You got 2 points for every CW or digital QSO you made, 1 point for phone, and we had a grid square multiplier because we wanted to encourage people to basically just flood the entire United States and across the eclipse path with HF signals. And there was an exchange, and then we really relied on the RBN, PSKReporter, WSPRNet, those to be our data sources for this. And so it was quite successful. We had 570 logs that were sent in, and we were able to parse in almost 30,000 QSOs, and in there were almost 5,000 unique call signs, 80 DX entities. So I'd say it was a pretty good success for an 8-hour operating event. And so here is the map. This is just of the RBN observations over that 8-hour period. So the little black dots here are the stations, the transmitting stations that participated. So if you were operating CW during the SEQP. You should be able to find your little black dot here. And then the blue stars are the RBN receiver nodes. And then the colored dots in between, those are the midpoints between transmitters and receivers, one dot for every RBN spot over the 8-hour period. It's color coded by the Eclipse obscuration percentage. So totality is 100% or 1.0 obscured. And so you can see totality runs right through the middle of the US there. And so to help make the analysis easier, we ended up just focusing on the things that were 90% obscured or more so that you can see what those spots look like there. Okay, so to help us do the analysis on this, I contacted some friends at the Naval Research Laboratory, and they had an ionospheric model called SAMI-3, and they had done some calculations to predict what the ionosphere would look like during the eclipse. And so I asked them for those predictions, those model outputs, and they sent them to me. And then I was able to make this ray tracing movie. And so what you can see, this is very similar. This is the same ray trace diagram I showed you before between AA2MF in Florida and WE9V in Wisconsin. But now it's a movie. And on the top, you have the SAMI-3 model without the eclipse prediction, and the bottom you have it with the eclipse prediction. So it starts off the same, but as the eclipse comes on, you'll see the electron densities be lower in the bottom one than in the top one. And you'll see that the connection, the link between AA2MF and Whiskey Echo 9 Victor disappears as the rays escape off into space when the electron density gets below the maximum usable frequency for that particular link. So here, I'll play this. And there you can see the eclipse has caused that effect. Now the eclipse is over and the link comes back. Pretty neat, huh? So that was great. So that's one connection, one time series of predictions, calculations between AA2MF and WE9V. But what we really wanted to do was we wanted to simulate, all of these connections. So we actually created another map where we put in a grid of, transmitter locations across the US. And we ran the model between every combination of transmitting location and every combination and receiver. And we did it for all four, for 1.8, 7, 1.8, 3.5, 7, and 14 megahertz. Those were the bands we focused on. We did that for the entire solar eclipse QSO party at a 3-minute interval, step interval. And then what we did was we did that on a supercomputer, and we counted up how many of those model runs predicted a link connection and how many did not for each of those paths. And then we plotted that. So what we have on top here is these are actual results from the solar eclipse QSO party from the reverse beacon network. And on the bottom, this is the model result. So on the top here, you can see this white dashed line. This is when an eclipse maximum occurred. And then if you go right here, this is 0 hours totality. This is an hour and a half before. This is an hour and a half after. This is the distance between transmitters and receivers. And then this is for the 14 megahertz band. And so you can see for a good hour and a half before the eclipse maximum, 20 meters it was pretty hot. People were communicating no problem. And then as the eclipse came on, you can see the number of communications dropped off until it got to a minimum. And then as the eclipse went away and the sun came back, the band recovered and people were able to continue communicating. And so that's just from the RBN observations. Down here, this is from the model, and it essentially shows the same result. So there are definitely differences in the model that still need to be explained. You see there's quite a bit more spreading here in real life versus the model. But there's quite a few similarities too. And so I'm only showing the 14 megahertz result here, but we do have on the HamSCI website the other bands and published in the Geophysical Research Letters paper as well. So you can actually see all the bands that we tested. Another interesting thing that happened with the Eclipse, WA9VNJ, who unfortunately is now a silent key, he made precision frequency measurements of WWV during the Eclipse. So does anyone here do the frequency measurement tests, the FMT? Where there's a transmitter that has maybe an unknown frequency, and your job is to figure out what that frequency that's being transmitted is with great precision. This is similar to that, but the idea is here we're listening to WWV. It's a standard station out in Fort Collins, Colorado, and we know that WWV is extremely well calibrated and stable to produce a 10 megahertz signal. So any variations we see in that, if you have a good receiver, any variations you see are presumably not due to WWV, and if your receiver is good enough, not due to your receiver, but due to the ionosphere in between, something that's happening in between the transmitter and the receiver. And so that's what W9VNJ showed. So he made these, this is the day before the eclipse. You can see, here's the 10 megahertz line. If you were sitting right next to WWV, you'd expect this to just be a straight line across. But that's not what we see. We see positive excursions in the morning hours, negative excursions in the evening hours, and a funny spike over here. Well, what I think is happening, and we're still working on understanding this much better, but what we think is happening at the moment is that in the morning when the sun comes up and the ionosphere starts to build up its electron density, you get the path length, the propagation path length gets shorter as the electron density gets higher. And when you get a shorter path length with time, that's like a positive Doppler shift. So that explains this positive Doppler shift over here. In the evening, when the sun goes away at dusk and the ionosphere becomes less dense, then you get less refraction and the path lengths get longer. And so that corresponds with the negative Doppler shift over here. During the middle of the day, things are more stable. What is this thing over here? Well, that corresponds, if you remember those solar flares we talked about before? At that same time, there was just an M0 class solar flare that happened right at the time, coincident with this. So we think there was a sudden flash of ionization there that caused a shortening of the path length. And that's where you're getting that frequency shift right here. On eclipse day, we see some very similar things. We see the positive Doppler shifts in the morning, the negative Doppler shifts in the evening corresponding with dusk. And then during the eclipse, you see the opposite behavior. So here we see the negative shift as the eclipse comes on, which is like going into dusk. You see the positive Doppler shift as the eclipse leaves, which is like going into dawn. And so there's your eclipse effect right there. That's the big thing. But I was perplexed for a while. What is this little jump right here? And so again, is this when Steve first sent me this graph, he sent me, it looked just like this and it said eclipse maximum right here. And I said, well, that doesn't really match what I think the eclipse should do. So it was like, is this S curve real? And so it is real, but it's not related to the eclipse. In fact, there's another solar flare. This is maybe a C2 class solar flare. And it shows up very nicely right here. So even these smaller solar flares can have an effect on the propagation that we have. So we are looking forward. There will be an annular solar eclipse in October of 2023. So 3 years from now. And then there will be a total solar eclipse in April of 2024. And so we're working on some things to basically, maybe we'll redo the solar eclipse QSO party. We'll probably be doing something a little bit different too, but we're hoping to look at ionospheric signatures during these eclipses as well. I wanted to show that, you know, we are making more precision measurements than even what we just showed you. Steve Serwin, WA5FRF, who is still very much alive and working right now, he just sent me this data from about a year ago when we had what's called the Festival Frequency Measurement, celebrating the 100th anniversary of WWV. And so he is in Texas making these measurements. And it's really, here is an actual spectral plot of the measurements, the spectrogram format. So now instead of just getting a single number characterizing what the received carrier is doing, we actually see a number of different, you can actually see multiple frequencies at the same time. So if you look right here, you see a fairly steady carrier right there, but then you also see these oscillations over here. So this oscillation here, this might be a traveling ionospheric disturbance, and you see that throughout the day. But then over here, that might be coming off of the F layer ionosphere, and this might be going off the E layer ionosphere. So this might be a good example of multipath. So this is another case that we're working on studying right now. And Steve has done a lot of great work on this. He actually just wrote a paper for the Tapper DCC explaining many of the different things he sees. And you can see that if you use something where you're just trying to calculate a single frequency off of this, like we're doing in FLDigi, you cannot capture all of this, all the things that are actually going on. So really nice measurements. So all of this is great, but can we do better? You know, the RBN, WSPRNet, PSKReporter, they weren't really designed from the ground up for science. What if we could create a network of personal space weather stations that were designed for both science and ham radio from the beginning? And so that's the idea for the HamSCI Personal Space Weather Station project. And the Personal Space Weather Station was actually, first person to kind of recommend that idea was Ward Silver, N0AX. He said that right after the Solar Eclipse QSO party is that this should be HamSCI's next project. So that's what we're working on right now. So what is a Personal Space Weather Station? It's a multi-instrument ground-based device designed to observe space weather effects both as a single point measurement and as part of a larger distributed network. It's personal because we're trying to design it so that any ham radio operator who wants to can purchase one and put it in their own backyard, operate it in their own backyard in conjunction with their regular ham radio station. So for hams, the PSWS, we needed to provide information about current radio propagation conditions, both locally and also as part of a global network. So we'll include things like FT8 monitors or WSPRNet monitors. That's implemented already. So in addition, we want the Personal Space Weather Station to also take into account the needs of professional researchers who want to study aspects of the ionosphere and space weather. So we have a very precision, we're including the design for making precision frequency measurements and having it be able to run exotic receiving modes to help understand the ionosphere. And this is a collaborative project under the HamSCI Collective, and it's being led by myself at the University of Scranton. And I have collaborators from Case Western Reserve University, W8EDU, the NJIT, New Jersey Institute of Technology, University of Alabama, MIT Haystack. Tapper is a huge collaborator, and volunteers from other universities and the amateur radio community as a whole. So what makes up a PSWS? Here's a basic block diagram. At its core, there's going to be a software-defined radio that's nominally going to go from about 100 kilohertz up to about 60 megahertz direct sampling. And so we really want this the idea is to have this produce just raw IQ samples. And then this can be processed by either an FPGA on board here or by a local computer in a number of different ways, perhaps simultaneously. So the same raw IQ output can be used to provide spectrogram snapshots of the entire HF band. It can be used to monitor standard stations, such as WWV. We might be able to use it as a passive ionoson receiver, monitor HF, HF signals such as FT8 Whisper and RBN, do HF noise characterization. we're trying to see how many of these modes we can develop and run simultaneously off of the same set of raw data. So this is the raw data up here, and then these are derived products. So of course you'll have an antenna. What kind of antenna, that's still up for debate. You know, at the very simplest, just even throwing up anything that can receive WWV will be effective for some of these studies, because as long as you have the precision frequency measurements and you can hear WWV, even a simple dipolar wire in the tree will help. If you're trying to do something more exotic, like determine O mode and X mode polarization, then you're going to need, or if you need to do something that's trying to observe calibrated field strengths, then you might need a more expensive or more exotic antenna setup. So we're still working on that over here. There's going to be a GNS, or GNSS is Global Navigation Satellite System. That's the generic for GPS, which is the US version of this. So we'll have a GNSS disciplined oscillator and total electron content receiver. There will be a ground magnetometer, which ground magnetometers are the things that are used to determine, what the KP index is and the A index. So, and they can determine much more than that. What they do is they actually sense the current systems that are going overhead in the ionosphere, in addition to other current systems and the Earth's main magnetic field. So we're going to collect data from there. All this will go into a single board computer for local user display, data reduction. It'll send the data off to a central server through the internet, and we'll have a public database. And then hopefully it's going to be modular, so we have the potential to add future instruments as well. We are planning both a performance-based and a low-cost version of the system. So the performance-based one is really the one that's being developed by Tapper, and they are designing from the ground up a brand new software-defined radio called the Tangerine SDR. And this is going to be FPGA-based, 0.1 to 60 megahertz direct sampling. It's modular, so it can have up to 2 RF modules on it, and each of those RF modules are designed to support up to 2 channels. So you can have potentially 4 phase-locked channels for this SDR. Right? To begin with, we're starting with receive-only cards, but they do have plans to make transmitter cards in the future as well. So we'll have that. For this, we'll have a dual frequency GPS, GNSS chip for the timing. So just definitely beefier specifications here. The target for this is, say, $500 to $1,000. And then the low-cost version is really focused just on making these precision frequency measurements of things like WWV and CHU on multiple bands. And that's going to be, Raspberry Pi based. They have a little Raspberry Pi hat that they've designed to go on top of that with this receiver. We'll probably have a single frequency GPS disciplined oscillator. You can still plug the ground magnetometer into it. So the target for this is closer, hopefully around $100. I think that's a bit optimistic at this point, but that is the goal. So how are we organized? I am at the University of Scranton. I'm the lead principal investigator of this project, coordinating everything else that's going on. At Scranton, we have a postdoc, Deb Joshi, KC3 PVE. He's working on trying to understand some of the science behind what we see. Jonathan Rizzo is an senior undergraduate student who's actually been a ham for quite some time, and he's also a non-traditional undergraduate student. So he's actually working in industry on semiconductor and is quite skilled. So he's actually working on helping to develop a very low frequency receive module for the Tangerine. And Veronica, she's an undergraduate student who's now the president of the W3USR Amateur Radio Club, and she's also been our summer research student this year. University of Alabama, Bill Engelke, AB4EJ, they are in charge of the software, both the local control software and the central database and the central control software. Tapper, they are Scotty Cowling, WA2DFI, is the chief architect, and he's got a number of people working with him. Tom McDermott, N5, EG, John Ackerman, N8UR. They're all working on the Tangerine. David Whitman, Jules Maddy, They're working on the magnetometer design. David Larson runs our Monday night telecons and the website. And so they're responsible for the Tangerine SDR, the data engine for that, and the ground magnetometer. Case Western Reserve is doing the low-cost personal space weather station. There's actually a lot of communication now between these two groups, so we're trying to make this as compatible as possible. NJIT is providing scientific oversight to the ground magnetometer, and my colleague and friend Phil Erickson, W1PJE at MIT Haystack, is also a science collaborator. So I think I'll go through these kind of quickly. These are the this basically where we are with each of the different components. Everything is still it's still basically in prototype stage at the moment, either prototype or design. So for the local software, local control software, there are prototypes that exist. Bill does have this up and running, and he has a number of modes implemented, including the propagation monitoring F3A and Whispers is running right now. And while he's still waiting for the Tangerine to be developed, he is able to use things like his Flex radio or a Red Pitaya as a substitute to do a lot of the testing on these different modes. Here are the specifications for the Tangerine SDR. You can see we're using an Altera / Intel Max 10 50,000 logic element FPGA. It's got 512 megs of RAM. You can see the data engine. It's going to take nominally 11 to 15 volts input. Here's the information on the RF module. So it'll be a 125 megasample or 122.88 megasample per second, 14-bit A to D. We have precision time stamping module, and we're expecting prototypes. We're expecting them this fall, any day. In fact, I'm about ready to place the order. For the magnetometer modules, I'm getting ready to place that. We're probably a little delayed on the prototypes, but we're getting there. Ground magnetometer being developed by Tapper and NJIT. Here's a picture of a prototype right now. And this week, I am getting ready to place the order on, so hopefully we'll have probably about 50 of these for testing soon. And here's the low-cost personal space weather station. So you can see there's this little hat that goes on top of a Raspberry Pi. So that's pretty much it. One of the things I want to point out right now is that this is a project that we are actively developing as a community. This isn't something I'm saying, okay, you can go out and buy right now. We meet every Monday night at 9 p.m. If you go to hamsci.org and you click the Get Involved tab, you can find our meeting schedule and you can join our listserv. And you can join us on Zoom for these meetings. We meet every Monday night at 9 p.m. to talk about the Tangerine SDR. We meet Thursday mornings at 10 a.m. to talk about the low-cost personal space weather station. Every other week on Thursdays at 3 p.m. Eastern, we have the HamSCI telecon to talk more about science. So people are actively developing these things right now and doing the design. So if you go to hamsci.org, you can get more information. Also, you can go to tangerinesdr.com and get more information about the project there, and you can join in. I think, there's always lots of acknowledgments. I get data from all over the place, and we need to try and acknowledge that. And we do have National Science Foundation grant support as well, which we're very grateful for. So I think that's about it. I'll say thank you, and I will take any questions.
Well, thank you, Nathaniel. And the K3LR antenna system will be very available to you once the Tangerine system is released. And we hope to be one of your flagship personal space weather stations on the network. And if you can release your screen, we will. That will take and tile us back to all of the folks that are here this evening. And Nathaniel, you want to talk about your national or your NSF grant of 1.3 million? Is that right?
Yeah, $1.3 million. So I think we were both skilled and lucky all at the same time. I don't know how much you people know about how National Science Foundation grants and academic grants work. But, you know, every once in a while, the funding agencies will put out a call for, you know, proposals to do various work. And about, I guess 2 years ago, we were talking about doing this personal space weather station, and I was working with Tapper, I was working with a number of other people, just coming up with these ideas. And we were planning on doing this no matter what, basically on a volunteer basis. And then the National Science Foundation came out with a call for what was called the Distributed Array of Small Instruments program. And what they wanted, this was specifically for the geospace community, they wanted the development of new distributed ground-based instrumentation. And so it just seemed like a slam dunk. You know, the budget was right. We had the HamSCI meeting going already where we were talking about doing this. So then I just took the proposal call. I went through all the HamSCI meeting presentations that were relevant, talked to the people who did the different components, and we wrote it up into a proposal, and it was funded. So here we are.
That is tremendous to have $1.3 million behind you from the NSF to make this happen. And I cannot wait. I mean, if you look at the hours in a day, I mean, I probably use this station here, which is one of the largest amateur radio stations in the world. Maybe I use it for 2 hours every day.
Yeah.
And so that means that there is many, many hours of research time that's available. And with the high-speed internet connection here, I'm just so excited about what you're doing there. And I cannot wait to be hooked up with you.
I think one of the things we're going to have to do, Tim, is do you know how they figure out what experiments to run on the big radar systems and the big telescopes in the world?
No.
No? Well, what they do is they basically have a call for proposals. So scientists who want to use those stations, they have to write up a proposal or plan where they state what they want to study and how they want to study it. And then the people who administer that particular telescope, Hubble telescope, or, you know, Arecibo Incoherent Scatter Radar, they decide which ones are really worth studying. So I think what we might have to do is we might have to have a call or a competition for what type of ionospheric science can we do with personal space weather stations at K3LR, and then try to pick the best ones and do that. What do you think about that?
Yeah, no, I think that's a great idea. And as this stay-at-home thing has gone on, more and more of K3LR will be available remotely, like turning rotators and selecting antennas. So I'm preparing for the ability for scientists to be able to take control and utilize what we have here. Do we have any questions for Nathaniel, our Eagle Scout PhD, and just a tremendous presentation here tonight, and the work he's doing at HamSCI. Any questions for Nathaniel?
When's cycle 25 going to get moving?
It should be soon, I think. They're just starting to see the first sunspots of the new cycle. So it usually takes a couple years for things to ramp up a bit. So I'd say probably somewhere between 2 to 5 years will be more on the upswing.
So Ron, the word on the street is, and of course this is all, you know, future stuff, so is that 2025 will be the peak. Yeah. But I wanted to ask Anne-Marie. Anne-Marie, I think you are Nathaniel's mother, is that right?
That's right. Very proud of him, obviously.
What's it like being the mother of Nathaniel?
It's great. He's a loving, faith-filled, kind person who really puts his heart in everything he does, and he's always been like that since he was a little child. So I'm very proud of him, and I'm glad he participates and encourages all the ham radio operators, because when he first started, we were worried, like, oh my gosh, he's talking to all these strangers, but then they all turned out to be friends. So it's really a blessing. He's great.
So
and I thank you for the opportunity to even listen in. I appreciate it.
Anne-Marie, we're thrilled to have you here. And, we have several other scientists on here tonight, amateur radio enthusiasts. And some of them used to take apart things when they were young and try to put them back together. Did Nathaniel do that?
Oh yes, many times. And he was always famous for trying to figure out how to do something different with ordinary objects. For instance, a nickel. He would try to see if a nickel would work in the back of a TV set and see what would happen to it. And what happened, Nathaniel, you could explain the rest.
Yeah, I think my father was watching a football game. And then I was like, oh, I can put this nickel down the back slot of a TV, just like you do at the arcade. And then my father wasn't watching a football game anymore.
But that was really funny. One we remember. And then the other thing is for birthday parties, he would have like build your own batteries. So that's one of his famous birthday party gatherings when he was little.
Well, I haven't heard that before, that you go to a birthday party and you're asked to build your own battery, but it seems to fit. And Anne-Marie, I have to congratulate you as a parent for raising Nathaniel into the fine human being he is and professor that he is today. And I was the one that nominated him for Ham of the Year at Hamvention. And I think the world of him, and I'm excited about, and he's just getting started. That is the thing that is so phenomenal. And the University of Scranton is such a lucky place to have Nathaniel out there leading by example and mentoring. And I was thrilled when he stopped here a few years ago, and we spent some time walking around, and I'm just, the future is certainly very bright for him. So, I did not know that you were going to join us tonight, but
I didn't either.
It's so great to have you on with us. And where are you located, Anne-Marie?
I'm in Bloomfield, New Jersey, about 2 hours from Scranton. And
Okay.
So that's where I am. And Nathaniel sent me the link just a few minutes before this started. So I thought, I'll just go on and, just see what he's up to. So it was really nice to be here, and I really appreciate the opportunity. And I wish you all the best, 88 and 73.
And Anne-Marie, even though Nathaniel looks like he's just 14, I understand you're now a grandmother because of Nathaniel.
That's right. I have a wonderful, wonderful daughter-in-law and a 20-month-old grandson who seems to be very attracted to all the ham radio and electronics that Nathaniel and Rachel have.
Well, that is great. And Rachel is very good as well, and very smart, and I've seen her present. And this HamSCI group that Nathaniel founded, and his workshops have been just off the charts. And again, he's just getting started, and I can speak on behalf of the Mercer County Amateur Radio Club. We're thrilled to have had him here this evening, and kind of the icing on the cake and the sprinkles have been that you were here to experience this as well.
Well, thank you. I truly feel honored, and I appreciate all that you do.
And so does anybody have any questions for either Nathaniel or Anne-Marie?
I've got a comment for Nathaniel.
Yes, Gordon, go ahead.
Yeah, I'm the faculty advisor for K8YSU, Youngstown State University's Amateur Radio Club.
Mm-hmm.
And we're going to see you in a school club roundup in October. How about that?
I certainly hope so.
All right.
We're working on it. We're still a very young club, so like we just started with like shortwave listening this summer.
Yeah, it's a ton of fun, and for them to practice what they're reading in books, and they can see how it works.
Yes.
So thank you, Dr. Forsara,
Thank
KZ3W. Any other questions or comments for Nathaniel?
I have a question. How have the fires out west and the smoke coming across the United States, even to Europe, how's that affected radio?
Ooh, I'm really not sure. I haven't had a chance to look at that. I can speculate some things, but it'd be very, 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 very speculative. So I don't know. That's something that's really good to look at.
Good question.
Yeah, it's an excellent question. Does anyone else know? I can tell you, so I spend a lot of time thinking about traveling ionospheric disturbances, and one thing that what I can say is that we know that certain things like large tornadoes, winds going over mountains, certain earthquakes in certain situations can create wave structures that can produce these traveling atmospheric disturbances like I was showing earlier. But exactly how that gets up to the ionosphere, it's not, that's still messy. That's not so clear in when it, when it happens. And that's a really big area of research right now. It's not like, like right now you ask me, well, what does a solar flare do to HF communications? I have a reasonably good idea of what they do, and I can show you. And I think, we don't have a consistently good understanding of exactly how what's happening on the ground affects the ionosphere. And that's one of the big areas of research right now.
Any other questions for Nathaniel? Well, Nathaniel and Anne Marie, thanks very much for joining us this evening. This was beyond my expectations. So thank you so much for your time and effort and all the things that you do, not only for your university students, but also for the amateur radio community and the dedication you have to HamSCI. And we look forward to hearing more about what you're doing, and we will welcome you back in the future.
Thank you, Tim. It's been a pleasure.
Okay. And with that, this Zoom room stays on until the last person drops. So, and that means with Alex, it could go on. Dr. Alex has got the hat on. He's ready to go. And so this could go on for 3 or 4 hours or 5 hours. I think the record is like 2:30 in the morning.
Wow,
So,
Tim, at this point, I'm going to say 73 and thank you.
I'm afraid I do too, because I still have lesson plans to do for tomorrow.
Okay.
I would love to stay, but
It's been a pleasure. Thanks.
Thank you, Anne Marie, and thank you, Nathaniel.
thank you.
And
But
but the rest of you, we'll stay on until until there's nobody left. And Josh, Hubbard, Josh, hope you get home from the soccer game here. But Alex has the DX hat on, so anything can happen.
Thank you, everyone. 7-3.
73, Nathaniel.
Thanks, Tim.
Tim, I have a question. Well,
Yes,
what a
sir.
great presentation. The young doctor there just, wow, what a great person going on there. But anyway, as we were in the Elmer station, in the Elmer section, you were talking about north. And I was following along until you said high noon. And then you took and made me get lost. You mentioned 11:43. What do you mean?
So if you look, if you Google what high noon means, that time actually changes every day, what high noon is. And high noon is a term for the time, and it might be 11:43, it might be 12:30, it might be 11:15. It depends upon the time of the year when high noon is, where the sun's shadow is directly true north.
So is that for specific location? Is that by a
Yes.
bearing and all, or,
It is.
or how do you find that?
You just go to Google and say, tell me high noon for September 22nd.
And it'll pick up my location and go from there.
Well, no, it will ask you your location.
Okay.
And will say, you know, and I mean, it's not the kind of thing where you have to put in your longitude and latitude, but if you get it for Youngstown, Ohio, you'll be fine.
I never knew that. Thank you very, very much. I thought high noon. Yeah, that was 12 o'clock at noon.
Well,
Now
high
I
noon.
know. Thank you.
You're welcome. High noon is when it's really noon, which means the sun is going to create a shadow that is true north.
Thank you.
Another way to think of that, Art, is when the sun is what we call at the zenith. So it's directly overhead, or at least on that plane of being directly overhead, and where it would cast a shadow true north.
Tim,
Yes, John.
I asked a navigator how the ancient mariners found high noon, you know, and he says, well, you just keep shooting the sun until it doesn't increase anymore. And at that spot where the angle between where you are and the sun starts going down, you just passed high noon. And it's different every day. And that's when they took, because they only knew latitude. And that's how they determined latitude, was their noon fix. And when they didn't have any instruments, they just kept shooting the sun until it stopped going up. And that was high noon where they were.
Right. Thank you, John. What else do we have? Harry, how did your antenna projects go over the weekend?
Well, I did some other work. Rather than putting up, I'm going to try putting another antenna up this weekend. The past weekend, I did some work on that. I finally used the Soda Beams mast. And I put that up with some guide ropes and some pulleys on the top. And that thing's a little bit whippier than I expected, particularly on the front. You really do need to guide that because it's very, at the topmost element on that is very much like a fishing pole. So if you put too much tension on it, it starts bending over a bit. But I got it up and I made some contacts with it. You know, first time I've done that. Unfortunately, the base is a little bit too big for the beach umbrella base that I have. But if you remember from field day a couple years ago, I have another mast that fits that one perfectly. So you learn things. So I made some contacts. I'm going to be up there again this weekend and do some more work on it. And at some point, I will put up that 40-meter half square as permanently as I can in the trees. That ought to put out a really great signal into Europe. I found that half squares are really good antennas. But with the 40-meter one, that's a big antenna, 66 feet long, and has to be at least 33 feet up in the air. And that's pretty high and that's pretty long. But it was a lot of fun.
So we're starting to ship the IC705 now.
That will be welcomed when I get one. Believe me, after I spent another 15 minutes hooking up. Don't get me wrong, I'm not knocking KX3s. They're good radios, but they just weren't designed for digital modes. They predated that. So I will be very eagerly looking forward to that. I'm going to keep the KX3, of course, because it's still good CW radio. But for digital modes, unfortunately, it's just, it needs some work. But yeah, I will be looking forward to that, for that 705, believe me.
Great. Alex, you got to help me out here. Got to carry this thing.
Hey guys, anyway, I'm going to get running along. Hey, I'll see you guys Thursday night. That was a great presentation. I'd love to get Pitt involved with his efforts, but our station is still down due to coronavirus. We need to get in there and do some work, and we really can't until the campus starts opening up a bit. But I would dearly, I know that Juan has an interest in this, and I'd love to see Pitt get involved with this weather, with the solar weather project. I think that'd be a good thing for Pitt to do, because we have an HF station that sits unused most of the day too.
Okay,
So,
well, make sure that Juan and the rest of the Pitt
oh yeah,
club get involved with HamSCI.
absolutely, absolutely. Hey, I gotta run. I'll see you guys later.
All righty,
Take
thanks,
care.
Harry.
Sure, you bet. Bye.
73. Okay, Alex, it's time for me to hand over the reins to you. You're on mute there, Alex.
I got the hat on, man. I'm going back to culinary school after that talk, okay? I have no idea what's going to happen here. The weather thing has totally overwhelmed me. There's the hat. Culinary school, here I come. You know, executive chef maybe.
No.
Radio.
No. There's no leaving this hobby now, man.
I'm in. I got the DX. I'm going to call this the DX dunce cap, because that's where I am. I'm in the DX dunce cap. Holy cow. Yeah, solar weather, eclipses.
Isn't he something?
Unbelievable kids.
Yeah,
brilliant kid. Unbelievable.
He's brilliant. That is absolutely the truth. He's really good.
I hate to say, I don't want to say somebody made me feel stupid, but I'm wearing the hat. Okay, that's all I can tell you.
Hey,
Alex.
Yes.
Hey, this is Josh. Can you hear me? Okay.
Yeah, Josh, go ahead.
Yeah, I mean, I agree with you. He's really a really young man, but remember, everything is relative. So if you handed him a scalpel and asked him to do an appendectomy, he would be just as lost. So don't worry about it.
Josh, I can teach you to do an appendectomy in about 20 minutes. No problem.
I still wouldn't trust myself, Alex.
No, you're the man, Alex.
No. Dunce cap. I got it on. That's it, man. I'm history. What can I tell you? I'm just history. You know, I'll see you guys. Maybe I'll cook you dinner sometime. That's all I can tell you. I'm selling my radios, taking down the antenna. I'm done.
Good grief, Alex. Hey, Tim, I wanted to tell you, I found a phone app that will give you true north based on your phone's magnetic compass and your GPS location. So it's really, yeah, so I'll have to show you, but very handy. So you can actually switch the app between magnetic north and true north, and it uses that combination of the magnetic heading and your GPS location.
Oh, that is great, and I know Bob would like that as well. And Josh, are you driving back from the soccer game?
Yeah, we're almost home. But Maria did great, but we lost 8-0.
Okay, well, as long as Maria had fun and she did great.
She did. We're very proud of her as always.
Great. And I'm so glad you got to see and listen in to Nathaniel's presentation. That was really special tonight.
Yeah, very, really fantastic in terms of the development of the Tangerine SDR and the personal space weather stations. I see lots of potential for that. So, and it's great that they have two different models that they're working on. The low-cost Raspberry Pi hat will make it very accessible for anybody to participate, really. And then the more powerful version for stations like yours. So very neat.
Yeah, all the way around. I think it's going to be good. So, and Alex, it was great to see the Steel Man here for a few minutes.
Oh, hey, you know, I miss my guy. You know what I mean? He's the second half of the dynamic duo. He's like Batman. I'm Robin. You know, what can I tell you?
Yeah, we gotta get him out of work in 16 hours a day.
They're killing him in there, man. They're killing him. I worry about him. You know,
Yep.
He's not 22 anymore, man. Working those hours.
What's the
Surgeon
status
hours,
of
man.
their
That's what
strike?
surgeon hours are.
What's the status of their strike? Do we know? Is it over? Is it
Well,
negotiated?
nobody's budging, Josh. They met. No, they're 10 yards apart, and nobody's budging. So they're going to go for a while.
Wow, that's too bad.
Yeah, yeah. Sad. So yeah, man, I enjoyed the talk. Couldn't understand half of it, but did the best I could. Put on the dunce cap. I'm there. All right.
Didn't you get the part where he said, "Hello, my name is"?
That's it. That's the only.
Yeah.
That's where it ended, right there. When he said, "Hello, my name is. Thanks a lot. I'm from this university." After that, it's all Greek, man. It's all Greek. That's all I can tell you. I mean, I can't even get my FL Digi to work, and I'm going to talk about solar weather. What can I say? Good grief.
There's expertise in lots of areas.
Oh, you know what? Thank God there are too. We need expertise in every area. There's no doubt about that. You know,
And whatever his was, I think he's really good at.
I think he's great at what he's doing, and God, more power to him. That's all. I agree, Marty. I agree with you. That's all. What can I tell you? You know, and I'm glad he's there, and I'm glad he's doing it because he's going to add to our fund of knowledge, and that's what we need, man. More building blocks. They're all building blocks. Everything you learn, you know. So Marty, I get a call by my daughter. I was on the phone with my daughter. So all her friends said, "It's your birthday. We're going to have a party at your house. We'll bring the food." Well, you know, my daughter is an infectious disease specialist down in New Orleans.
Right.
She goes to work, and her boss is reprimanded her because she had 14 people at her house, and the maximum is 10. So he's in trouble.
My daughter had to buy a new cell phone this weekend.
Oh.
For different reasons than most of us do. She was hoping to resign from her job on Monday, and she had $1,000 in technology that had to be spent. And so she walked in, and her boss informed her that she was not only going to do her own job, that she was taking over the job of this other woman who had quit. And my daughter informed her that she was also leaving, as well as 2 other people.
I'm dropping the bomb. Nothing wrong with that, man. You got to drop the bomb.
Seven people have left so far, and 3 have contracts to leave.
This might be a trend. You know, maybe there's some problem here. I'm just making a wild ass guess. You know.
Well, we use WAG and Psych too.
WAG is okay. You know?
It's good. When you don't know what you're talking about,
we use WAG and ham radio.
You know.
How much WAG and ham radio is there?
You know, so she wouldn't tell me she's not allowed to tell me how many people are on the project. But the whole company only has between 65 and 70 people.
There you
10
go.
are leaving as of now.
Holy cow.
They have an affectionate term for the boss, the head boss, the owner.
Richard Cranium?
They call her Hitler.
Hitler. Adolf.
No, just Hitler.
Nice.
Just by the last name.
Where the hell's Hitler? Nice, nice.
So she said the woman was going to talk to her today. She said if she offered her $100,000 more, the answer was no.
So here's the question. How do you start team building when your team thinks you're Hitler?
I mean, she started blaming my daughter and her supervisor that everyone was leaving and doesn't realize it was her.
Oh God! Like I said, how do you start team building when everybody thinks you're Hitler? I mean, what are you
So
going to build up an SS troop or what?
she's got 3 weeks and then she's history.
Well, you know what? You know what? Sometimes you just got to go when you got to go, man. That's all it is, you know? That's all I can tell you. No doubt about that.
So that's a little humor.
Yeah, my daughter's boss, he had a talk with her about how many people she had and everything. You should have said half of them were inside, half of them were outside, so they were socially distanced. We're all good. You know, you got to think quick on your feet, right? Good grief.
Sometimes you need to know better too. I don't know.
Yeah.